Hello everyone, welcome to the Electronics and Signal Processing module. So today we're going to be talking about signals, transducers, and basic electronic components. So I know some of you might be thinking this is a chemistry course, so why are we learning electronics? And that's reasonable. And we'll answer it today. The short answer is that every analytical instrument that we've looked at so far, from the UV vis to the atomic absorption, works because of electronics converting chemical information into numbers on a screen. Understanding that makes us a better analyst. So by the end of this, we'll have completed these learning objectives. So we'll be able to look at the sort of like the bigger picture idea of what things might be. In this, we'll be looking at some like componentry. We'll be looking at some of the laws that are important, and we'll be doing some actual calculations on this. So what we'll go through is we'll look at an overview of the module, we'll look at the signals in analytical chemistry, we'll look at transducers and so on, all the way through to our usual worked examples, the way that we always finish off our lectures. So where are we at now? So in module one, remember that we covered the fundamentals of measurement. So we did calibrations, figures of merit, method validation, some quality control, some quality assurance, and all of those things still apply here to this module. In modules two and three, we looked at how we can get information about molecules and atoms using different types of spectrophotometry. And every time that we had a measurement there was a detector which captured that interaction. And then somehow we got an output. How that output was generated is what we'll learn in Module 4. On the right-hand side, we'll see the lecture outline for this, and we'll try to go through and make a understanding of exactly how those signals that we get from our samples get turned into something we can read. So what exactly is an analytical signal? Well, it's any measurable quantity that carries information about your sample. That's the key phrase. It carries some information. Signals come in different domains. They can be electrical, such as a voltage or a current. They can be optical, such as light density at a certain wavelength, thermal, mechanical, chemical, and all of these are signal domains. All of these work. So think about the samples that you already know from the earlier modules, such as UV vis, where the signal starts off as light intensity and then some is absorbed by our species of interest, and then we measure how much light is left. In AAS, we're counting photons. In FTIR, we record an interferogram. In a pH meter, we'll measure a voltage. We haven't got that far just yet, but that is a direct voltage measurement. And so every single one of these ultimately gets converted into an electrical signal for processing. That's what we're looking at here. The electrical domain is going to be combining or connecting everything together, okay? So this diagram is a map of signal domain conversions, and we look at how every domain, chemical, optical, thermal, mechanical, all points towards the electrical domain. Okay, that's critical there. So this is at the center, and it's not a coincidence. It reflects the reality of how instruments are designed. We're very good at using electricity, and so that's what we fall back on to get accurate measurements. So each arrow here is labeled with the type of transducer that performs the conversion. An ion selective electrode converts chemical activity to voltage. A photodetector converts light to current, and so on. Let's consider what a transducer actually is. So it's a device which is going to convert a signal from one physical domain to another. That's all it is. So we classify these in two types, input transducers or sensors, which convert a non-electrical signal into an electrical one. And these are what we use in our analytical instruments. A photodiode, for example, converts light into a current. A photomultiplier tube, a PMT as we know it, takes a single photon and amplifies it into a measurable current pulse. A thermocouple generates a voltage proportional to temperature. A piezoelectric crystal changes frequency when mass is deposited on it. That's how a quartz crystal microbalance works. Then we have our output transducers or actuators. These go the other way. So these take an electrical or non to a non-electrical signal. An LED converts current to a light. A heater converts current to heat. These are less central to analysis, but still part of the instrument. For example, the deuterium lamp in a UV vis is an output transducer driven by an electrical circuit. So this is the key idea. So every instrument you've studied has at least one input transducer producing an electrical signal proportional to the analyte property. That proportionality is what makes quantitative analysis possible. So let's take this information and ground it in the instruments that we've already covered. So here we have a table mapping out the input signal, the transducer, and the electrical output for the 7 instruments. For UV vis, we have light intensity going into a photodiode or PMT. For IR, we have infrared that hits a pyroelectric all the way down to GC. Now, GC, we haven't covered quite yet, but it's important that we are aware of it. So this one is using FID, which is a flame ionization detector. It produces a current on the order of picoamps. That's 10 to the minus 12 amps. This is really, really small, and that needs serious amplification before it can be digitized, which is exactly why we'll need op amps, and that's going to be covered in lecture 2. The bottom block lists the 5 desirable properties of any transducer: sensitivity, linearity, selectivity, stability, and fast response. These should sound familiar. They mirror the figures that we discussed in Module 1. That's not a coincidence. The transducer is the first link in the measurement chain, and its quality limits everything downstream. This is a very important slide because this block diagram applies to basically every analytical instrument that we encounter. There's a sample, transducer, signal conditioning, ADC, a computer. That's basically the chain here. So let's go through it. So on the left, we have the sample being excited by some source, whether it be light, heat, voltage, whatever the technique requires. The sample's response then is a physical or chemical signal, which is captured by the transducer, creating a pretty weak electrical signal. That signal then goes through conditioning, such as amplification, filtering, possibly current to voltage conversion. The conditioned analog signal is then digitized by the ADC, and the digital data flows into the computer for processing and display. Now look back at the brackets at the bottom. So today we're going to be focusing on the transducer block and building the vocabulary for the components. Then lectures 2 and 3 will cover signal conditioning and ADC, and in lecture 4 we'll deal with the noise that contaminates every stage of the chain, okay? So I want you to remember this diagram. So whenever you're troubleshooting an instrument, your question is going to be, where in the chain is the problem? Is it the source? Is it the sample prep? Is it the transducer, the electronics, the software? Having this mental model turns you from someone who just presses buttons into someone who can actually diagnose issues and can contribute to the maintenance and upkeep of instruments in the lab. Okay. So why can't we just plug the transducer directly into the computer? And that's because the raw signal is almost never ready for digitization. The signal could be too weak, might be the wrong type. It's almost certainly contaminated with some noise from the power line, from thermal fluctuations, from nearby equipment. The baseline might be drifting, the response might be nonlinear. Signal conditioning addresses all of these. Amplification makes the signal larger, filtering removes unwanted frequencies. Current to voltage conversion changes the signal type, and all of these operations are performed by circuits built from the components we're about to learn. We'll cover the details in lecture 2 when we discuss the operational amplifiers. For now, just understand that this block exists and why it's necessary. Okay, before we dive into the components, let me address the why directly. As an analytical chemist, you need to read instrumental schematics for troubleshooting. You'll encounter specifications like input impedance, bandwidth, and noise figures. You'll need to communicate with instrument service engineers, and ultimately, you'll also need to be able to diagnose whether a problem is chemical, such as bad sample prep, interference, or instrumental, such as a failing detector or a noisy amplifier. What you do not need to do is design circuits from scratch or solder circuit boards. That's for electrical engineers, and our goal here is literacy, not fluency. On the right, you'll see the 3 passive components: the resistor, the capacitor, and the inductor. These are the building blocks of every analog circuit inside every instrument, and we'll have a look at them one at a time. So resistors oppose current flow. That's all they do. They're pretty simple. They convert electrical energy into heat, which is why they're used to limit current and divide voltage. The fundamental relationship is what is called Ohm's law, so where V equals I times R. So the voltage equals the current times resistance. If you know any two of these, you can find the third, and this is the most important equation in electronics, and it's beautifully simple. Power dissipated by the resistor is P, which equals IV. Okay, so which also equals I squared R or B squared over R. This is important because you're choosing components. A resistor that dissipates too much power will overheat and fail. In instruments, resistors set the gain of amplifier circuits, convert current to voltage, which is exactly how photodiodes output gets turned into a measurable voltage and creates voltage dividers for reference signals. They come in values from 1 ohm up to 10 mega ohms, which pretty much covers everything from 1 to 5% tolerance. So resistors can be in series or parallel. So the same current flows through each one, and the total resistance then is simply the sum. So the Req equals R1 plus R2 plus R3 plus R4 plus R5s and so on. And the total is always larger than any individual resistor, and so voltages add up across the chain. When resistors are connected in parallel, i.e. side by side, sharing the same two nodes, the same voltage appears across each one, and the currents add. The equivalent resistance is found by the reciprocal formula. 1 over Req equals 1 over R plus 1 over R plus 1 over R3. The total is always smaller than the smallest individual resistor. Think of it as giving current more paths to flow through. These two configurations are the building blocks for analyzing any resistive circuit. Sorry. So, Gustav Kirchhoff gave us two laws that combined with Ohm's law let us analyze pretty much any circuit. So, Kirchhoff's voltage law, or the KVL, says that the sum of all voltages around any closed loop is zero, which is think of it like hiking trail that returns to the starting point. All the elevation gains and losses must cancel out. In the circuit diagram on the left, the source voltage Vs minus the voltage drop across R1 minus the voltage drop across R2 equals zero. Kirchhoff's current law, the KCL on the right-hand side, says that the total current entering a node down here must equal the node or must equal the current which is exiting the node. Current is conserved. It doesn't pile up or disappear at a junction. On the right, I1 plus I2 equals I3 plus I4. Like these laws might seem a little bit abstract at the minute, but they're the reason your instruments work reliably. So every circuit designer uses KVL and KCL to ensure signals are processed correctly. So this one leads us on to the voltage divider. So the voltage divider is one of the most practical circuits in electronics, and you'll see it pretty much everywhere in instrument design. The idea here is relatively simple. Two resistors in series are connected between a voltage source and the ground. The output voltage is tapped from the junction between R1 and R2. The formula is V out equals V in times R2 over R1 plus R2. So think about what this means. If R2 is much larger than R1, most of the input voltage appears at the output. If R2 is much smaller, almost none does. You're choosing the fraction of the input voltage you want. In instruments, voltage dividers generate reference voltages, scale signals to fit the ADC input range, and form the basis of Wheatstone bridges used for precise resistance measurements, which we'll be looking at in a worked example. Capacitors then are the next one after resistors. So these store energy in an electric field between two plates. The charge stored is Q equals C times V. But the really important relationship here is the impedance formula, where X sub C equals 1 over 2 pi FC. Okay? This tells us that a capacitor's opposition to current decreases as the frequency increases. So how does this get applied practically? So a capacitor blocks direct current, DC. It won't let constant current through, but it passes AC. And the higher the frequency, the easier it passes. This is basically the basis of filtering. In instruments, capacitors filter noise, couple AC signals while blocking DC offsets, produce timing in RC circuits, store energy for flash lamps, and maintain voltages in sample and hold circuits during ADC conversion. Typical values range from picofarads to millifarads. The choice depends on the frequencies you're working with. Then the last one then is inductors. So inductors are the complement of capacitors. They store energy in a magnetic field created by current flowing through a coil. The voltage across an inductor is L times dL over dt. It opposes changes in current. The impedance is X sub L is equal to 2 pi FL. And so this is going to increase with frequency. So inductors pass DC freely, but resist high frequency AC. So they're kind of like the opposite of capacitors. And so that's the key insight. So capacitors and inductors have complementary frequency behaviors. Together, they form filters that separate signal from noise. This is going to be really important in lecture two. And on how this applies to analytical instruments is that you'll see inductors in RF coils for NMR, in the induction coil of an ICP torch, and in transformers for power supplies. They're less common in signal processing circuits compared to resistors and capacitors, but they play critical roles in specific applications. Okay. So let's have a summary of our components. So the three passives that we make use of in a common instrument are the resistor, which dissipates energy, impedance independent of frequency, capacitor, which stores energy in an electrical field, where impedance decreases with frequency and passes high frequencies. And then in the inductor, which stores energy in a magnetic field, where impedance increases with frequency and it passes low frequencies. So the bottom block states the key insight. The frequency-dependent behavior of capacitors and inductors is what makes filtering possible. And filtering is how we separate the signal we want from the noise we don't. Every instrument in the lab uses this principle, okay? So before we move on to the worked examples, let's have a little look at some of the common symbols. Being able to read a schematic is like being able to read a chemical structure. It's pretty much the language of electrical engineering. In the top row, we have the resistor, which we've just covered, the capacitor, and the inductor, all of which we've just covered, okay? So the resistor is a triangle, the capacitor is two parallel lines, and an inductor is a coil. In the middle row, we have voltage sources, so we have a direct current, we have an alternating current, an AC current with a sine wave inside, and the ground symbol here, okay? Then at the bottom row, we have some active components such as a diode, which allows current in only one direction, an op amp or an operational amplifier. This is a triangle symbol that inputs with a plus and minus inputs and one output, and this will be important in our lecture two. And then the third one here is switch. You don't need to memorize, of course, each one of these today, but you should be able to recognize these in an instrument manual by the time you're done. Okay, so let's apply what we've learned, and here's a practical scenario. So you have a temperature sensor that outputs between 0 and 5 volts, but your ADC can only accept up to 3.3 volts. If you feed 5 volts into that ADC, you'll damage it, and so you need a voltage divider to scale the signal down, okay? So what equation do we need here? Well, we start with the voltage divider equation. So V out equals V in times R2 over R1 plus R2. We know V in is 5 volts, and we want V out to be 3.3 volts. We'll choose R1 plus R2 to equal 10 kilo ohms to keep current draw reasonable. Substituting 3.3 equals 5 times R2 over 10,000. Solving for R2 gives us 6,600 ohms or 6.6 kilo ohms. Then R1 is 10,000 minus 6,600, which is equal to 3,400 ohms or 3.4 kilo ohms. So ultimately, you choose the nearest standard resistor values, which would be 3.3 kilo ohms or 6.8 kilo ohms. The output voltage would be slightly different from exactly 3.3 volts, but reasonable enough, close enough. This kind of practical rounding is normal in circuit design. This is a real scenario. Microcontrollers in modern instruments commonly run at 3.3 volts, and sensor outputs often exceed that range. Number two, then, this is where we have a network with R1 is equal to 100 ohms on the top branch and R2 equals 200 ohms in the series with R3 equaling 300 ohms on the bottom branch. What's the total resistance between points A and B? Okay, so here we need to identify the topology. So R2 and R3 are end-to-end, i.e. they're in series. So their combined resistance is simply 200 plus 300 equals 500 ohms. And we'll call that R23. Okay, so the step two now is to then use R1 and R23 to share the same two nodes, A and B, i.e. they're in parallel. So we apply the parallel formula, 1 over Req equals 1 over 100 plus 1 over 500. That gives us 5 over 500 plus 1 over 500, which equals 6 over 500. So Req equals 500 over 6, which is 83.3 ohms. Okay, so let's check it. The parallel combination must be less than the smallest individual branch resistance, which is 100 ohms, and our answer of 83.3 ohms checks out. So always do this to make sure that everything is working as we expected. Okay, all right, so today's key takeaways are here. So analytical signals exist in multiple domains, but are almost always converted to electrical signals. Second, transducers are the bridge between physical or chemical world and electronics. Third, the DAQ block diagram, transducer conditioning, ADC computer applied to every instrument. The next one then, the three passive components, resistors oppose current, capacitors store charge and block DC, inductors store magnetic energy and block high frequency AC. And then fifth, Ohm's law and Kirchhoff's laws are the foundation of circuit analysis. And the last one then is voltage dividers are a practical building block for scaling signals. And so these connect well to module 2 and 3, where we had photodiodes, PMTs, and thermocouples. And every detector is a transducer, followed by some sort of signal conditioning. All right. Then next time, we're going to be talking about analog electronics. So that's our operational amplifiers, our op amps, and our filters. And then make sure to always check the practice problems. Solutions will, of course, be posted, but make sure that you're at least aware of them, you've read through them before you look at the solutions so that you have a rough idea of what equations you need to use and also the strategy for solving these because these are critically important to remember. All right. If you have any questions, please leave them down below. I will get to them or email me. Thank you very much.